Okay, welcome everyone. Thank you for coming to our NSF Cyber 2A webinar. Before I go ahead to introduce today's speaker, I would like to give you a brief introduction on our Cyber 2A project. So the Cyber 2A is an NSF-funded project to provide cyber training to geoscientists, in particular Arctic scientists, in modern artificial intelligence techniques. Our project's long-term goal is to establish a sustainable and scalable learning community, and this will be accomplished through customized training in cutting-edge AI for both current and next-generation geoscientists who are also interested in applying AI to solve scientific problems. And one of the activities we are hosting is a Cyber 2A webinar series. And this webinar series is co-created with the NSF NNA Permafrost Discovery Gateway project, which aims to connect Arctic scientists, geospatial scientists, AI experts, our industry and community partners to foster cross-disciplinary conversation and innovation to empower the next generation geo-AI scientists. And today we have the great pleasure to have invited Dr. Xiaogang Ma to share his research in large language models with open geoscience. And before I started to introduce Dr. Ma, we will launch a pre-webinar survey. It only have a couple questions to collect your interest and familiarity with today's topic. And after the webinar, we will also launch another survey to see how much of your knowledge has been improved and also your interest for future topics, similar topics. And we will also have like a poster survey, which we will launch right after Dr. Ma's talk. And if you have to leave earlier, you are very welcome to enter the poll before you leave, or you can leave it until after our QA session. Okay, thank you everyone for providing input. And now I will give a brief introduction on our speaker, Dr. Xiaogang Ma. Dr. Xiaogang Ma is Associate Professor of Computer Science at University of Idaho. He received his PhD degree of Earth System Science and GI Science from University of Twente, Netherlands in 2011, and then completed postdoctoral training of data science at Rensselaer Polytechnic Institute. His research focuses on deploying data science in the semantic web to support cross-disciplinary collaborations and scientific discovery with broad interest in complex systems in Earth and environmental sciences, data interoperability and provenance, and visualized exploratory analysis of big and small data. And I have known Dr. Ma since like 2011 when we just got to graduate school. And since then, Dr. Ma has been a great peer role model for me, who I look up very much. So I'm super excited to have invited Dr. Ma to give our webinar today. Okay, Xiaogang, the floor is yours.
Yeah, first, thanks a lot to Dr. Wenwen Li for this invitation. And it's a great pleasure and also a great honor to introduce our recent work to the Cyber 2A community. I saw several familiar names in the participant list on the Zoom meeting. So hopefully we can have a lot of discussion after my presentation. My talk will be focused on our recent work on the Mindat open data service. Mindat is online and open database in the field of mineralogy. But since our recent work has been focused on the semantic enrichment, and also very recently I think for about 1.5 years, we have been working on large language model application. So hopefully we can share some mutual interests with the Cyber 2A community. I will first briefly introduce a number of concepts. We got those kind of understanding, definition, or experience from our research projects in the past, I think almost 10 or 15 years. The first is, what is semantics in geoscience? I think many of you may have seen this diagram before. But in general, from the left to the right, you can see a number of those representation types, from very simple, like a catalog, a glossary of some concepts in a domain, to, for example, on the right, very complicated, formal, logical assertions for concepts, relationships in a domain. And also in geoscience itself, we can see all those kind of representation types. Like on the left, you can see glossary of geology, and even in the Japanese, a few months ago, I was in Japan for the JPGU. I also use this as an example of it. In Japanese language, they also have those kind of syntactic rules or representation structures for all those concepts in geology. And on the very right, you can see a recent example is, I think this is a collaboration between Geological Survey of Canada and also USGS. People build a formal ontology to represent a number of topics in geoscience. And then here you can see a diagram. We use those 3K approaches to represent like methods or technologies people are using in data science, deduction and induction. I think in other words, you can also call this deduction knowledge-driven approach, induction data-driven approach. Sometimes if you are talking about machine learning, you can call them supervised machine learning or unsupervised machine learning, or just like a mixed usage. That's why we also have a concept called abduction. It's just like an exploratory approach. But we have those kind of discussions when we talk about methods in data science. Later in the work of Mindat, I probably can do a quick reflection. We'll mention some examples of our data science results. And then, because I was teaching semantic web and open data here at the University of Idaho. Actually, in this semester, I will teach semantic web and open data again very soon. We'll start next week for the class teaching. So very often I hear questions and comments from students and also from other colleagues, for example, in ESIP, in AGO, in GSA, people asking, you talk a lot about semantics, you talk a lot about ontologies, vocabularies, but what are the actual functionality? What are the actual usage? What are the actual like value of using semantics in data science for geoscience? So I use this diagram. I just first use, you can see in the center, a process of data science, a lot of those steps in data science from data collection, data cleansing, and then exploratory analysis, confirmatory data analysis. When we see confirmatory data analysis, we mean using some statistics, machine learning approach to get a good result, and then visualize your result, publishing, and then making decisions. But then when I look through a number of those projects I participated in the past years, and also a number of other projects I observed or studied in my own literature review or research, I can make like a brief. Sometimes I can say it's like a biased match between those projects to some steps in the data science procedure, because I think many of the projects, they can be related to several steps, but just in my own understanding, I can say, okay, this project has a really highlight of using vocabulary for data search or discovery, like schema.org is a good way to do metadata annotation and then help the search engines to index them. And then, for example, Google has Google Data Set Search. That's a good way to help people to find data. And then, for example, on the right, you can see the object-based image analysis. Nowadays, it's called semantic segmentation. I think this is a good way people use semantics. Even a very simple structure like land use types, people are using this semantic representation in machine learning and deep learning approaches. So I did a kind of this, I believe if we just use this simple list of steps in data science, we can collect more examples. Here is just a few of them I personally know, and I was using this in my introduction of semantic web, ontologies and semantics to undergraduate students and graduate students. But since we are talking about application of semantics in Mindat, so when I was preparing this talk, I also did a brief summary. I think those boxes or the work in this box with green color, those are some of the works we have already finished, or at least ongoing, or at least with some achievements or progress. And then those boxes in the light yellow, light blue color are some of the work we plan to work on. So I think in today's talk, I will talk mostly for those work we have already finished. So basically those boxes in green color, like what we have done with metadata annotation, and then some of those large language model assisted for data query, LLM assisted data exploration, and then the work we have done with the unique identifiers, and then some result with the visualization and the initial data analysis. But I'll also briefly talk about like our vision or our plan for the next step, like what we have already done. We have some initial result with the LLM assisted knowledge extraction, knowledge graph construction. Okay. So I will talk about Mindat work. So here is a background introduction to Mindat. I think in the Cyber 2A community, some of your work might also be focused on data curation, data management. I believe here there can be some mutual interest with Mindat. Mindat is an open database for mineral species. So basically species and also their distribution on Earth. But recently we also have mineral species for other planets, like for Mars or for the Moon. It has been there for almost 30 decades. Xiaogang Ralph created this database in the 1990s when he was still a high school student. And then he actually created university to chase Mindat as his dream. And I sometimes say, oh, you're so lucky. You made your interest as your lifetime career. And now Mindat is very popular among the geoscience community, actually also among the general public. You see, we have about 24 TB data sets, a lot of web pages, but the usage is very high. For example, in last year, for the website itself, there's a number of 60 million page views from around 10 million unique users. And then most of the data sets, they are kind of crowdsourcing. The website now has about 86,000 registered users, and then among them, about 9,000 got the requested this high-level access. So about 9,000 of them, they are data contributors. So basically, this means they can upload records to the website. And then the database also has about 1,000 volunteers from across the whole world. We call them data curators. Many of them are like professors, retired professors from universities. Some of them, they are research scientists in museums, either like a public museum or university museums. And then they help review the uploaded records and then make sure the quality is okay before the records are matched into the main database. So there's a kind of workflow to get the data set and also make sure the data quality is okay, and then release the data set. And then along the 3 decades, it's just get more and more popular among the users, including experts and also the general public. And then about 4 years ago, we saw the increasing needs from especially the research community. And that's why I applied the Open Mindat project. I was a PI, but the work is a collaboration between ourselves at the University of Idaho and then the technical team of the Mindat database. And also we have collaborators from Carnegie Institution for Science doing some data-driven research on mineral ecology and mineral evolution. In the past 4 years, we have achieved basically some progress in 3 or 4 parts. The first part is we did a really good review and cleansing of the records, including some semantic enrichments I will introduce later. And second is we built the API for the open data service. Originally, the Mindat website is open. You can browse. You can also use an interface on the website to query and then to download records. But for I think 2 decades, there was no machine-readable or machine-accessible API. But through the Open Mindat project, we now establish the API. So for anyone who has some coding skills, you can access the API directly. And then the third part is we have participated and coordinated some discussion on community standards among the geoscience, for example, in petrology, like classification of rocks, and also in mineralogy, the mineral species list, basically some community standards in geoscience. Now people can use the API to output those machine-readable, standardized, either like a mineral species list or rock classification directly from the database. And the last work we have done is we built some really good data-driven discovery use cases based on the data set made open from the website. So now let me show you some of our recent work on the semantic enrichment. So when we begin the Open Mindat project, we did a really quick review of the key data subjects or topics within the database. You can see mineral species absolutely is the most important topic in this database. Oh, I think that they probably can be some students or early career scientists in the audience. The diagram you see here, we call them a concept map or conceptual map. It's a very simple one, but very fundamental skill, but I believe it's still very useful if you are working on semantic representation or database curation. I think this is the very first step when you come to a database and you want to know the topic within the database, the subjects in the database. So you see we have mineral species and we have mineral group, the interrelationship between them. And then we have rocks, and then the relationship between mineral species and the rocks. And then another very important concept or data subject in Mindat is locality. Basically, you can call them locations. That's also fine. But more formally, we call them locality. I think this is a geospatial concept. And then if a mineral species is found at a certain locality, we call it a occurrence. You can also call it a mineral observation. That's also fine. And within Mindat, people even define a concept called loss entry. I think loss entry. Basically, it means you find a mineral species at a locality. It's called an occurrence. And we have images. And Mindat also imports some records of fossils from other databases. This is related to paleontology and geobiology. Okay, but these two, locality and mineral species, they are the 2 top concepts. And then if you dive into the details of mineralogy for certain mineral species, you can see a lot of those attributes. Each of them can be a research topic, I believe. So here I will not talk details about them. Okay. And then on the database, when you are using just the front end, you can already see all those detailed attributes. In database, we call them attributes, and then we can use, for example, a UML, Universal Modeling Language diagram to represent them. But I would like to also call them semantics, right? They represent the meaning of a mineral species. Like here for quartz, you can see so many attributes. And then in our work for data review and data cleansing, we also look into many community standards. Like here, globally, there's International Mineralogical Association. They take care of the work to review and ratify all those new mineral species. So whenever I say people say I found a new mineral species, you need to submit an application to prove what you find is indeed a new mineral species. And then there's a scientific procedure within this association. They approve it. So they take care of the reviewing and the ratification of the mineral species. But then the Mindat technical team, they are always tracking the progress from this international association. And then they upload other detailed records about each mineral species in their database. And some other organizations, like the British Geological Survey, they also took the initiative, for example, for the rock classification. They already used SQS, Simple Knowledge Organization System, to build the vocabulary in a machine-readable way. Actually, it's RDF. And we have also embedded those kind of machine-readable formats into our database. And in the field of mineralogy and also the broad geoscience, people have also done something on the scientific topics. For example, Dr. Bob Hazen and his colleagues, recently they have built the so-called paragenetic modes of mineral species. And from our side, when I discuss with the Mindat technical team, I would say this is just like a knowledge system. If we look at it from a perspective of semantic technology, we call this as a knowledge system because this is like it's like a representation of people's understanding about the paragenetic modes. And we have also embedded this structure into the Mindat database, and we have and based on this, we can even build some data analysis and prediction outputs. I will show you later. Okay, so let me show you some examples about the outputs after we embed those kind of semantic technologies. What are the advantages and what are the outputs? So here is one output. Is I think many of you may have heard about schema.org, but Facebook actually has a very similar initiative or approach called the Open Graph Protocol. It's also for the metadata annotation of data sets on the internet or on the web. And then within Mindat, we have already applied Open Graph Protocol. For example, if you see a mineral species, here the mineral species name is called overnight. If you just see the page source code, you can see how the Open Graph Protocol annotation schema is used within the source code of this page. You can see like metadata, property type, and then website, and then URL, and then here we can even show some thumbnails of the mineral species overnight. But then what is the advantage of this? Search engines, they can index this, and then they can have this in their database. And when you do search, for example, on Google, because they already have the index metadata in their own database, so they can quickly show you the result. So the advantage for this is usually whenever you search mineral species or mineral occurrence records, usually the Mindat page will be either, I think, the top 3 or the top 5. Usually, and at least the Mindat page will be on, the first page of the search result when you search on Google. And also because Open Graph Protocol is the initiative of Facebook, it's even more convenient. For example, if I paste the Mindat web URL for overnight, if I paste it on my Facebook timeline, Facebook will automatically generate a thumbnail. For example, they will use the link in the metadata for the thumbnail image and then generate like a kind of structured thumbnail for the information you can see on the Mindat website. So this is an advantage of those kind of syntactic level using semantic technologies. And also the unique identifiers. I think in the Mindat database, the backend is MySQL. So it's already a kind of relational database. If you have experience with relational database, you know, usually for any defined subject, in the database, or just for, like, for example, for a single table, we need a primary key. And then the primary key on the individual record level, the record should be unique. So actually, when Mindat was built as a relational database, there are already those kind of unique numbers or record for each subject, like here for the minnow species codes. Actually, there's already a unique Mindat ID for it. But just because we have several, or actually a long list of data subjects in Mindat, we have minnow species, we have localities, we have minnow occurrence. Now we also have fossil types, we have fossil records, and many others. If you only look at this sequential ID, sometimes the number might be similar. For example, 3337. You can see how this is minnow species codes if you only take this as minnow species. But in locality, they can also be a locality with the same number. So within Mindat, we use a kind of structure. If you look at the left, Mindat is also like a namespace prefix. It's just like a short name for the URL, mindat.org/. And then we use several other numbers to represent the data subject and the data type, and also the organization who first defined this record. So this is a kind of structured way we used in Mindat to represent each record as a kind of unique existence within the database. And we can also make them resolvable, like here for Mindat, colon 1, colon 1, colon 3337, colon 0. This actually is a URL and is resolvable. And then because we have access to the MySQL database, we can also generate a UUID. This one is just like a test. We are able to generate also a UUID for each of those unique record in the database. So before we apply this resolvable URI or URL for this, within the MySQL database, we already have this. We already have the unique identifiers, unique numbers. I believe you can understand. But now, just based on the MySQL, we can also generate these resolvable URLs or URIs for the front end, the website. And then the back end, for people working on the Open Data Service API, which we can also use this identifier as an entrance to query database or data records from the API. That's one advantage. And based on the API and the Open Data Service, we have also built Python and R packages called Open Mindat. Basically, 3 major groups of functions. The first one is the most popular and then I think highly requested from the community, is automatically output minnow species list. And then the second is some detailed queries functions. Based on different combination of conditions, people can query geomaterials, including minnow species, minnow occurrence, and others. And then the third one is the localities. And those are already made open on Siren and PyPy. People can just download them and then install in Python and R and then begin to use them. And as said, we actually have some discussion with other geoscience data portals like GeoRock, EarthCam, and also the community of One Geochemistry to coordinate those kind of standards. Now within the package, we can already output many of those machine-readable community standards like minnow species list, rock type classification. Like here, if you see the source code in the R language, it's very simple. You just type one line of code, minerals IMA list. You can get a detailed list of those IMA, International Mineralogical Association approved minnow species list. And one advantage of our work is because the API is linked to the database in the backend, and the database is always updating. I think now for the backend database, especially for the IMA approved mineral list, it's updated almost every 2 weeks. So if you are using the package, if you're using the function, you can always get the most up-to-date minnow species list. This is one advantage using those kind of open data service. And within those open data, we can do some interesting data analysis, including visualization. Here, I will quickly show you a number of examples. The first is we call it association analysis or association visualization based on the minnow species and the minnow occurrence record at a locality. Like here is a locality in the state of Maine. It's a county called Newry. And in this locality, there's already a list of 135 minnow species discovered. And there are a lot of photos. And many of those photos, you can actually see they are specimen photos. Specimen means samples. Okay, specimen is different from species. Species is the study of minology. Specimen means the actual samples. Like here, this photo is a photo of a specimen. And you can see within this specimen, people have already recognized 3 types of minnow species. Okay, and now we have 489 specimen photos for this locality. And many of those photos, there are more than 1 minnow species identified. Like for this photo, you can see there are 3 minnow species identified. So with those kind of records, we can do an interesting visualization. We'll call them frequency of minnow species co-occurrence pairs. So basically, we have so many photos, and in many photos, you can see the co-occurrence of minnow species. And then we can do a quick statistics to show the frequency of co-occurrence. Like here in this diagram, the size of each node is a minnow species. And then the size of them means the frequency of co-occurrence of this minnow species with other minnow species. And the link, we did not show the size of the frequency of co-occurrence, but in the size of the node, you can see the frequency of co-occurrence for this individual minnow species. So this is a kind of way, actually, I think the idea here is from the social network analysis, but just for each locality, we can do such a visualization. I think that, yeah, the next slide I can show you is the same locality. And then if you come here, if you come to this link, you can first see a list of those minnow species found here based on the specimen photos. And you can see the result of a force diagram. You can zoom in, zoom out, you can pan. And you can select which minnow species is the most popular here. And usually quartz is the most popular because quartz is just so popular, I think, almost everywhere. And if you don't want to see this scientifically meaningless minnow species, we have a slider on the top. You can just slide to the left. This will remove some of the most popular minnow species from the network. In that way, you can see in more details. So there's a kind of interactive visualization to show more details about the minnow occurrence at this locality based on the specimen photos uploaded by the community, and also the species identified in those images. Some of you may already have a question like, why we have so many labeled images for a certain locality? That's the advantage of crowdsourcing mechanism. We have a lot of users who can make edits to those photos. And also we have experts who review the results. Even for example, those labeled photos, they're not done randomly by anyone. Actually, there's a process of edit and reviewing and merge to the main database. And this locality for sure is a unique place because it's a very good mineralization zone, and there are a lot of people actually working in this area. Okay, and then the last, I will show you 2 other examples. The first one, I probably will call it data-driven. So it's also minnow association analysis, but now based on the co-occurrence records, Sean Morris and Anirudh, they use a kind of machine learning approach. Besides, just like a visualization in the previous slide, Now they can use a machine learning approach to first to summarize the association rules, the patterns in the association. And then in the next step, they can, based on the rules, based on the patterns summarized from the original records, they can make predictions. Like if you give me a new locality, and you already have a number of minnow species found at here, and based on the patterns in the existing minnow species, we can make predictions like which new minnow species can be found at here. And the Xiaogang have applied this approach to all the localities. We have more than 400,000 localities on Mindat, and now for any of them, we can get a result of new minnow species prediction. I will show you one example later. And then the second data intensive approach, for this one, I would call it deduction or knowledge-driven. That's why, because Dr. Bob Hazen and Dr. Sean Morrison, they first studied all the minnow species. Because at that time, there's at least about 5,600 of them. They studied all the minnow species. They studied the diversity, distribution, and also they studied their formational environments. And then based on this, they summarize a list of 57 paragenetic modes, basically patterns about why some minnow species are found together or formed together. There's a list of 57 of them. And then Xiaogang also applies this to all the localities. And based on the modes, we can make predictions. So now if you give me a new locality, and then based on the list of minnow species found at this locality, we can make predictions about the paragenetic modes at this area. So people studying minnow deposits or mineralization, they have interest to see this. So let me show you the exact results when this is applied. So yeah, here is a quick view of the so-called paragenetic modes. On the horizontal bar, you can see a list of 57 paragenetic modes. And then in the vertical dimension, you can see a list of, this is a list of 5,656 minnow species. If you see a tag, basically means this minnow species is a part of net paragenetic modes. And some of them, they even have like a higher weight, is kind of representative minnow species for that mode. If you don't understand mineralogy, just like me, it's fine. You can just treat this as a knowledge model, okay? It's just like a classification made by experts. And now we come back to this locality again, Nuri in Mianyin. There's already a list of 135 minnow species found here, okay? And then based on this, using the association rules from Sean Morrison and Anirudh Prabhu, we can make predictions about possibly unrecorded minnow species. And then also based on the rules, we can even select how good is the match. Like for calcite or some others, they have very, very high percentage of match. So there's a high possibility. Just because this minnow species is not recorded at this locality yet, we cannot find a minnow occurrence for this certain species. But if you're interested, for example, if you're a graduate student, if you are a researcher of another area, you probably can see whether you can find a specimen, a sample of this minnow species at there. And then for the paragenetic mode, the result actually is simpler. How did we generate this score for the paragenetic modes? It's just like a reverse statistics, okay? Now we have a locality, Nuri. We have a list of minnow species, 135 minnow species found at here. We just check the paragenetic mode model provided by Dr. Bob Hazen and Sean Morrison. If a minnow species at here belongs to a paragenetic mode at here, we just add some points, we add some scores to that mode. So at last, you can see for the mode 34, it has a really high score, basically because the representative or basically the minnow species in that mode, many of them, they already found at this locality called Nuri. That's why this mode has really high score. Okay, so for any of the 400,000 localities, we can do such a prediction, minimum species and predicting mode. Okay, but in all regard, again, this is just like a very initial step of data intensive study. This is just like statistics or data-driven results. If you want to look into more details, if you really want to make some meaningful prediction or results, for sure you need to embed more geological background and then other studies to make more scientifically meaningful results about mineral species or the types of mineral deposits. Okay. And in my last 5 minutes, let me give you a quick overview about the work we've done with large language models. As I said, we have just worked on this for about 1.5 years. So I think the result to some of you is still very simple, but let me show you, because our focus is not, for example, our focus actually was not on, for example, the advantage of the algorithm or developing new algorithms for large language models. Our focus is on the usage, because Mindat already has such a big number of users. So our very initial idea is whether we can use large language models to develop, for example, a natural language interface for people to do data queries and analysis. On the left, you can see the architecture we designed. So basically 2 types of agents for the LLM application. One is supervised agent, and the other group is the so-called task agents. The supervised agent basically take the user input in natural language, analyze it, and then allocate those tasks to different agents in the task agents, and then get a result, evaluate it, make sure the result is good, and then return the result to the end user. Okay, I think this is a very, if you have already worked on LLM recently, you probably can see this is just like a very general architecture for using large language models in domain-specific applications. But just in our work, because in the past 4 years, we have already done something on the API, the data query. We have already achieved some other initial result in visualization and analysis. So for the task agents, actually we can reuse a lot of those existing use cases and examples from the source code of those use cases. But just for the supervised agent, we've done some work to use, for example, prompt engineering to make sure it understands those domain-specific needs, like here, some certain conditions to retrieve the mineral species. And then another work we have done is, because the first work we did is with just GPT-4o, and then we thought probably if you really want to deploy this to the Mindat website, we probably want to use open source LLMs. So in our second study, this was done about 1 year ago, we transferred to Llama because it's open source. But we did something interesting. Is in the first step, we used GPT-4o to generate a large number of those synthesized data sets, and use those synthesized data sets to fine-tune Llama. And finally, when we deploy Llama to do basically the same work, like association visualization, and then retrieve the locality and visualize the heat map to show the density of the locality, we can get more or less the same result comparing with what we have achieved with GPT-4o. So this is the second work we have done. And very recently, I think this was just in the recent 6 months, between myself and a postdoc, we conducted another work. Is we use large language models to build a pipeline to extract data records, knowledge items from, we call them the literature legacy. Basically, a lot of those either scanned or readable PDF documents. You can see a workflow here. First is Again, this is just a lot of those task agents to do different types of work. OCR, optical character recognition with the scanned PDF, and then named entity recognition, and then transform them into machine-readable format, RDF, resource description framework. And the last step is to align the entities we recorded from the PDF documents with some community level standards like geoscience ML, and then other vocabularies like mineral species list from IMA or rock classification. And also, we have built a kind of pipeline to do the quality control. And this is exactly what we are doing now. We want to build like an end portal, just like a part of the Mindat website, to make this open to the end users. Originally, they can use an interface on Mindat website to set up like conditions for querying and find certain mineral species. But now they can just type, just like ChatGPT, they can just type in natural language, I need this mineral species with this element, with some other element in a certain mineral group. They can type this request just in natural language. So this is what we are doing exactly now. But since we face a lot of these requests, and we also have had a lot of discussions with the end users, I believe we will have a lot of other works to do. We recently just got a new project funded by NSF, and this is part of the work we want to do. The first is use LLM to do data rescue. In this visualizer map, you can see the situation of the current Mindat records. On this map, you can see the locality records. You can see for North America, Europe, Australia, they have relatively better density of locality records. And if you look at, for example, China, Central Asia, Africa, and South America, actually, the number of locality records, they are still very high, but just the density is relatively low, and we believe there's a really big potential for increase the locality records in this area. And similarly, if you see this map, is we can also see a bias in the mineral occurrence or the number of mineral species found at each locality. Like here is the top 500 Mindat localities with the most recorded mineral species. In our original study with the Open Mindat project, we have already identified some reasons like why there's such a bias, like why for some certain localities they have very high mineral species records, but for some other localities, seems the number of mineral species found there is relatively low. I think there are many reasons. First is, for example, the language people use to study mineralogy, and second, for example, is people's desire to study or to find new mineral species. For example, actually for a certain locality, there can be many mineral species existing there, but just those are already known or existing mineral species. People don't have an interest to study them again. So there are many records missing at among those localities. So in our next step, we will also only enrich the records at this level. Okay. And the very last, I very want to share one of our experience doing those kind of data intensive work, either on data rescue, semantic enrichment, or data intensive scientific discoveries. Absolutely, we need to bring people from different disciplines, from different disciplinary background. Like here in the Mindat work, we have people in AI, we have people in data science, we have people in data curation, we have people in mineralogy, we have people in mineral exploration, people in geology, even people in ecology. So how to build a culture to facilitate those kind of collaboration, especially how to bring young people into the collaborative team. We have done a lot of work. Here is just like a kind of informal summary, okay? If you really want to run a good data song, especially those data zone to aim a domain-specific data-driven result, you need to bring the right people, basically people with expertise in data management, people who can find the right data records, people who can write code to do machine learning or statistics, and people with the domain-specific knowledge who can interpret the result. And besides those very serious scientific activities, you also need, as a leader, you also need to organize some kind of social activities to make everyone feels comfortable and then feel like comfortable to discuss and then to share the expertise and to work together. So I believe many of you know what I mean. Okay, so but this is what we have done in the I think past 10 years, and we have achieved a really good result. And that's why we call Mindat and open Mindat as a kind of community effort. So to wrap up my talk, I probably can see two parts. The first part is data and semantics themselves. I would see data and semantics, the very fundamental requirement is structure. Okay, I say this three times. Structure is very important. Either the structure in the definition, the structure in the database, the structure in the metadata annotation, or the structure in many other parts is very important. And then machine-readable semantics is not only about representing the structures, it's also about using the structures, using the definitions, the relationships to do reasoning. That's very important. And then semantics in data science, we also can see the importance of semantics for the so-called fair data, findable, accessible, interpretable, reusable. But if we look at the data science or the data analysis, semantics can be used to collect those steps in data science. And in knowledge, we can also infuse semantics in statistics, in machine learning to do better work. I think that's why in the semantic web community, now there's a approach, people call it neurosymbolic. And actually, this is also called knowledge-infused machine learning or knowledge-embedded machine learning. So this is a new trend in this field. Okay, I will stop it here. And I will be happy to answer any of your comments and questions.
Cool. Thank you so much, Xiaogang. This is a very eye-opening talk. And also congratulations to your recent NSF project. That's amazing to have the support to move forward the open mandate forward. Okay, so do we have any questions from the audience? And at the same time, we can enable the post seminar survey. Feel free to either leave your question in the QA section or please feel free to raise your hand so we can enable you to speak. I think there is a question in the Q&A, Marshall.
Yeah.
Types from Li Kui. What types of AI agent tools are you using? And what challenges should future users to be aware of when working with AI agent?
Yeah, I think probably you are talking about the large language model application in what I just presented. Basically, in the architecture, we designed, there are two types of agents. I think they are very general architecture when people use large language models. The first is the supervisor agent. Basically, this is the agent to take in users' requests in natural language and then analyze the requests and parse them into different tasks and then assign them to another group of agents. I call them task agents. And the task agents, many of the fundamental data analysis or visualization functionalities, actually they're built upon the work we did in the past. Basically, it's like, if you give me the detailed attributes or parameters to query a data set, we just translate them into SQL query and send back to the backend database. And if the task is to visualize a request piece of data set, we just call, for example, call a library in Python, for example, for the network analysis and visualize the result. So there are basically two types of agents in our large language model application, supervised agent and task agent. And because this is domain specific, so we built the agent on top of GPT-4o in the first use case. And then for the detailed data analysis visualization, we build upon our previous use cases.
Cool. Thank you, Xiaogang. There's another question from Ying.
Thank you, Professor Ma, for the great presentation. I think you might mention it, but I couldn't catch it. So what AI model did you use for the detection of mineral species?
Oh, the detection of mineral species. In the first use case, we, as I mentioned, we use GPT-4o, but for the detection of mineral species, actually, the procedure is not so complicated because the name of mineral species is very unique. And sometimes I even make jokes with my students. I say the entropy of mineral species name actually is very low. It's very low. It's very unique. So whenever people mention mineral species name in natural language, in the data request, we can very easily find the record. It's just like a unique identifier for the mineral species. But in some other situations, if the end user in their data query, if they did not mention exactly the name of a mineral species, for example, they just mention the chemical composition, for example, a number of elements, they say, okay, I want to see a list of mineral species with copper, with oxygen, with hydrogen, but without aluminum, without potassium. In that way, we can use these kind of conditions as the way to do the data query. So basically, it's not such a complicated process as you might think. The supervised agent just translates the natural language into database query and then pass them on to the task agent to do the database query.
Thank you.
Yeah, but in our future work, yeah, maybe this is related to another work. As I mentioned, in our future work, we also want to do, I think this is also partly related to multimodal or multimodal AI application. One of our ongoing work, I think we're going to start this very soon, is to apply semantic segmentation to the scene section images. Basically, it's like the images taken by microscopes, and then from the images, we can automatically recognize some mineral species based on the spectrum and based on some other patterns. This is also another research topic.
Thank you. That's very cool.
Yeah, sounds very exciting. And well, we are like 1 minute over time. There are still a few questions that hasn't answered yet, but we have got those questions recorded, and we will share with Xiaogang, and hopefully we will send you the answers in a batch. So you have Dr. Ma's email address at the bottom right corner of this slide. So feel free to contact Dr. Ma for your questions. Yeah, again, if you haven't participated in the post-survey poll, please do so. And let's do a round of remote applause to thank you, Dr. Ma, for the very fantastic and fabulous talk. And thank you, everyone, for joining us today.
Thank you for your time.
Bye. Bye, everyone. Bye, Xiao.